Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you on numbers 12, 13, 14, and 15 in your homework over magnetism. So number 12, it says, a laboratory electromagnet produces a magnetic field of 1.65 Teslas. Now, yours might say a different value, that's what mine says, but I set these up to generate random numbers. A proton moves through this field with a speed of 6.06 times 10 to the 6 meter per second. And it says to find the magnitude of the maximum magnetic force that can be exerted by this proton, or exerted on this proton. So the magnetic force is calculated by taking QVB, but the V needs to be perpendicular to the B. And what that means basically is this. If we had a magnetic field that pointed this way, if your velocity vector was this way, there'd be no magnetic force. If your velocity vector is this way, you get the largest magnetic force. If the velocity vector is somewhere in between, you get something kind of in the middle for a magnetic force. So the maximum possible magnetic force on a charged particle will occur when the velocity of the particle makes a right angle to the magnetic field. And the numbers here are just given. Just take your velocity, that's going to go there. The magnetic field strength given in the problem, that's going to go there. And then the Q is the charge of the proton, positive 1.6 times 10 to the minus 19th coulombs. You're going to get a number here. It's going to be very, very, very small. Part B, what's the magnitude of the acceleration of the proton? So by Newton's second law, the net force is equal to mass times acceleration. Take this force that you found in part A, use that for the net force. Then this mass will be the mass of a proton. You have to look that up. I'm going to let you do that. I'll give you a hint though. You'll end up with times 10 to the minus 27th kilograms, but I'm not going to tell you the front number. I'm going to let you look that up. Then it's just a matter of solving for the acceleration. You're going to get a really, really big number. So don't be surprised if you see something like 10 to the 12th or 10 to the 13th or something like that on that acceleration. So that's pretty much, I think, enough for number 12. Get rid of the stuff here. All right, so number 13, it says an electron is accelerated through 2600 volts from rest. So what that is, that's a difference in potential. 2600 volts. And remember that a volt is a joule per coulomb. And it then enters a region where there's a uniform magnetic field of 1.8 Teslas. So basically what that means is this electron started here. There's some sort of electric field. Now the reason I know is because electric fields go hand in hand with electric potentials. You can't really have one without the other. So this proton is accelerated by that field. So here's kind of a picture of the proton later, and it's going to be moving this way with some sort of speed here that I'm going to call V. And again, that's going to be speed in meter per second. So the first part of this problem is a work energy problem. If I write out the work energy theorem for this, PE1 plus KE1 plus work equals PE2 plus KE2. The proton starts from rest. The only force acting on the proton is due to this electric field, and that's going to put a force to the right on that proton. And that force is equal to the charge of the proton times whatever the electric field strength is. Now it turns out we're not going to need that anyway, because this potential, this difference in potential, takes this effect into account. So long story short, this force will be taken into account with potential energy term related to this, so we don't need to worry about any work terms. So what we get is basically PE1 is equal to PE2 plus KE2, which I'm going to go ahead and write 1/2 mv squared. Now, if I move this term to the left, this is going to read PE1 minus PE2 equals 1/2 mv squared. This is effectively the difference in potential energy for the proton. Now look at the electric potential here. This potential difference is given to be 2600 joule per coulomb. You just have to know what this is. Remember that electric potential, that's what this thing stands for, is defined as potential energy per unit charge. So that means potential energy is equal to charge times potential. And that means the difference in potential energy is equal to charge times the difference in potential. This right here is the difference in potential energy. This is equal to the charge times the difference in potential. This is the charge of a proton, 1.6 times 10 to the minus 19th coulombs. This number is the 2600 joule per coulomb. Notice if you take coulombs and you multiply by a number with units of joules per coulomb, you get joules. This is the difference in potential energy. And then this is just a 1/2. This is the mass of a proton. Look that up, and you can solve that equation for v, for the speed. Once you know the speed, and you're going to get a big number, this will probably be like, 10,000 or maybe 100,000 meter per second or something like that. Once this is a known value, then the magnetic force is given by QVB. And again, that Q is the charge of a proton. The V is the velocity you just calculated. And then the B is the magnetic field strength given in the problem. Now, part A, I'm going to take note, it says to find the maximum force. This equation would give the maximum force, and that will occur if this velocity makes a right angle to the magnetic field vector. B says the minimum force. Well, this really isn't a math question. This is more of a fundamental or a conceptual question. Imagine that when this proton enters this region, imagine that it does so parallel to the magnetic field, and then ask yourself what the force is. And that should be enough to answer that question. So the tough part about this one is you have to calculate the speed first using principles of work and energy. And you have to realize that this difference right here, this is the potential energy per unit charge. If you just take this thing and multiply by the charge, you're going to get the change in potential energy of the proton, and that's what this would be right here, the PE1 minus PE2. All right, so that should be enough on that one. I'm going to call that one done and kind of move on. All right, number 14. Get rid of this stuff. All right, it says a uniform magnetic field of 0.34 teslas is directed perpendicular to the plane of a rectangular loop. So what they mean is there's some sort of uniform field. I'm going to go ahead and draw my field this way. So these arrows are representing the magnetic field that they're talking about. The reason I'm drawing quite a few of them is because it said uniform in the problem. I want to draw enough in my picture here to show that it's kind of a uniform field. So you'll notice that as I draw these, I'm trying to space them about the same distance and so forth. So these are vectors that are representing the magnetic field vector. And the magnitude is 0.34 teslas. Now, in a standard XYZ coordinate system, right, this is what we would call the minus k direction in that picture. That's not going to be super important, but I thought I would just tie that to unit vectors if you watched any of my videos on how to talk unit vectors. All right, then it says there's a rectangular loop in this field. So I'm going to go ahead and draw that. I'm going to draw that in blue. And it says that it's perpendicular to the plane. The magnetic field is perpendicular to the plane of the loop. So what they mean is that these arrows are all perpendicular to this area here. That's what they're talking about. All right. And then this dimension here is some sort of length given in the problem. In the one I'm reading, it says 11 centimeters. And then the width is given in the problem. The one I'm reading, it says 8.5 centimeters. All right, and next it says find the magnetic flux through the loop. So in order to do that, you have to know how magnetic flux is calculated. So magnetic flux, that's this symbol when you look through in most textbooks. I don't know why they use that. It's a Greek letter phi, but the magnetic flux is equal to the magnetic field strength times the area. But it's important that the magnetic field you use be perpendicular to the area. In this case it is, so we don't really need to worry about that. Everything is good. Life is good. So what you want to do is just put the given magnetic field strength here. That's given in the problem. And then the area is the area of a rectangle. That's length times width. But you're going to want to be careful about that. This was given in centimeters and centimeters. I would convert these to meters first. For example, this one is 0.11 meters. And then I'll let you go ahead and convert that one. And then calculate the area, put that value here, and this will work out to have units of Tesla meter squared. And that should be enough. Again, what's important about this problem is what magnetic flux measures. It's a measure of how many field lines go through this area. So in my picture here, I've got like 2, 3, 4, well, maybe about a half and a half. So it's a measure of how many of these field lines are going through the area. Notice that if I made the area larger, more field lines would go through it, and that would mean you'd have a larger magnetic flux. All right, so that's probably enough on 14. Let's call that one done. 15. Find the magnetic flux of the Earth's magnetic field of 5 times 10 to the minus 5th Tesla through a square loop of 40 square centimeters for the following. Okay, and then there's an ABC. So first of all, let me talk a little bit about the picture. Get rid of this stuff. All right. It's talking about the Earth's magnetic field. I'm going to go ahead and just draw that, I don't know, maybe to the right. It doesn't matter which way it goes in my picture. So I'm going to imagine a uniform magnetic field. And the magnitude of that field given in the problem is 5 times 10 to the minus 5th Teslas. And it says we're trying to find the field through a square loop. Part B, it says when the field is perpendicular to the plane of the loop. So what they mean by that, it says square loop. So I'm going to kind of draw a square. It's important to understand the viewpoint here. I mean this in such a way that the magnetic field vectors are all perpendicular to the plane. That's what they mean by that. And then the cross-sectional area is given in the problem. The area, it says in my problem, is 40 square centimeters. So when you calculate the magnetic flux, right, that's going to be magnetic field times area. One thing you want to do is be sure that this area is in square meters. So the first thing you're going to have to do is convert this 40 square centimeters to square meters. So let me talk about that conversion. You might start with a fact that there's 100 centimeters in 1 meter. But this will not quite get it done because you'll notice that there's centimeters squared up top and 1 centimeter at the bottom. If I actually multiply this as it sits, my units would be centimeter, meter, and that's not what I want. I want meter squared. So the trick is knowing to do this. You square your conversion factor. Because now unit-wise, you got square centimeter divided by centimeter squared. So these will actually cancel by the time you square that centimeter there. And then you're left with meters squared. So you're going to get a pretty small number in units of square meters. Then this value will go here. Calculate your magnetic field. All right, part B, it says when the field makes a 35-degree angle with a normal to the loop. Honestly, part B is actually beyond the scope of the class and requires a little bit of trigonometry. I'm not going to ask that you folks do part B. I'm going to go ahead and I'll just give you credit for having it there, but that's not one that I want you to, that you really need to know how to do. The thing is, when I choose these problems, they don't allow me to change the A's, B's, and C's. So part B is not going to be required. Don't worry about it for now. Part C, when the angle makes a 90-degree angle with the normal to the plane. Here's what they mean in part C. They basically mean that this is now turned like this. And you notice that the magnetic field points this way, and you notice that none of it actually goes through the area here. So this one's really more of a conceptual question, right? You shouldn't need a calculator to answer that, but that's what they're talking about. And when they say 90-degree angle with normal to the plane. Normal means perpendicular. So this direction right here is normal to this plane. So what they're saying is the magnetic fields are this way, and they make a 90-degree angle with this normal to the plane. And again, all of that's not super important. The big thing to realize, this is the orientation, and none of these magnetic field vectors actually go through this area, to answer number 15. All right, so that's probably enough on those. I'll go ahead and make a separate video about other types of problems. I hope this video helps you get these homework problems done. Have a great day.